Okay, good evening. This is Professor David J. De Los Reyes. It's February 27, 2023. The time is 6:44 p.m. Okay, I will check my calendar. Okay, my lesson for tonight will be an interesting topic for tonight. This is one of the most complicated problems in electrical transients. Okay, and this falls under the study of advanced mathematics. Okay, let's proceed. My topic for tonight is advanced mathematics, lesson number 14. It's lesson number 14. We are on the application, and the circuitry for tonight will be a series RC AC circuit, meaning we are given a resistance and a capacitance connected in series, energized by an alternating current source, and that alternating current source is actually designated by E, and the voltage of the equation is actually E sub m sine of the quantity omega t plus angle P. The given circuit for tonight is an alternating current, okay, and the parameters involved are actually a resistance and the capacitance. Again, I will check my camera. Okay, we are fine. The problem is asking for current as a function of time. The last time around, I discussed RLAC. So for tonight, we are discussing RC AC circuit. Okay, let's proceed with the solution. Taking the summation of voltages around this closed loop upon closing the switch. That is sigma notation, the capital letter B, and this should be equal to 0, meaning the summation of voltages and this should be equal to 0. Okay, this is plus E minus B sub R minus B sub C, and this should be equal to 0. The voltage of the source should be equal to the voltage across this plus the voltage across the capacitance. That's the meaning of this, and this should be equal to 0. Substituting values, E is actually E sub m sine of omega t plus angle P. This voltage is actually sinusoidal, okay? It is represented by this. And this should be equal to, I will transpose B sub R and B sub C to the right. The voltage across the resistance is IR, it will be the current passing times the value of the resistance. The voltage across the capacitance, we have derived already this one from the previous discussions, that is 1 over C, the integral of I dt. So actually, we are given an equation involving an integral of I dt. So for us to bring out a differential equation without the integral sign, okay, what contradicts an integral sign is actually the so-called differential sign. So we will take the differential of all the terms. Differentiating or taking the differential of all the terms. For the left-hand side, this is a sine function, right? E sub m is constant times the sine of quantity omega t plus angle P. So it seems we are taking the differential of a constant times a function. So it will be that constant times the differential of derivative of that function. So it should be equal to omega times E sub m times cosine of omega t plus angle P times the differential time. How come that comes out? The differential of a sine is cosine, so this is now cosine. But the differential of the total angle is actually, okay, sorry for this one, there should be omega t over here. There should be a t over here. This should be omega t plus angle P, okay, times differential time. And this should be equal to, for the right hand side, omega is the differential of the angle, okay, times E sub m. The differential of sine is cosine, so this is now cosine. The differential of the right hand side should be R is constant, current is variable. So if we take the differential, it should be that constant times the differential of the current, or it should be R times di plus I dt over C. Okay, I have said from the previous lessons that, hold on. If we take the differential of the integral of I dt, because we are taking the differential of both sides, the differential of the integral of I dt, okay, this will cancel out. Okay, so what remains for this part here will just be simply 1 over C times I dt, or simply I dt over C. And to simplify the resulting equation, we will multiply all the terms by 1 over the product of R times differential time. Okay? There's a reason for that one, because we will try to make the first term to be simply di dt. Because if we multiply R di plus times the quantity 1 over R dt, this R here cancel with this. Okay? So what remains will be di over dt. So this is now di over dt. For the second one, this one, this dt here cancel with this. So what will remain? It will just be simply I, okay, times 1. The bottom portion will be the product of R times C. So this is actually 1 over RC times I. Okay, and this should be equal to, for the resulting right hand side, actually this came from the left hand side, I just rearranged. So this should be omega E sub m over R cosine of the quantity omega t plus angle P. Okay, because we will divide this by 1 over R dt. So this dt here cancel with this, so there is no more dt here. So what will come out will be double omega E sub m over R times the quantity cosine of omega t plus angle P. This dt here cancel with this. So there is no more dt over here. So actually we are now given this differential equation here. It's a first order differential equation. The left hand side is not so complicated, but unluckily the right hand side is not equal to 0. So actually the resulting equation is non-homogeneous differential equation, and it is actually first order. First order differential equation, it's non-homogeneous since the right hand side is not equal to 0. So to compute for current as a function of time, we shall try to bring out two solutions, the complementary and the so-called particular. Okay, let's go with the complementary. As always, the complementary solution is k e raised to mt. First derivative will be km e raised to mt. I will check my camera again. Still fine? We are given IC now. We are given the first derivative. We'll go back here. We'll substitute values. So what comes out will be km e to the mt plus 1 over RC, and following this, times k e raised to mt, and this should be equal to 0. And if we try to multiply all the terms by 1 over k e raised to mt, okay, first one times this k here will disappear, right? E raised to mt will also disappear. So what remains on the first one will just be simply m. For the second part, 1 over RC k e to the mt times this total thing will disappear, right? So what remains will just be simply plus 1 over RC, and this should be equal to 0. R is the resistance, and C is the capacitance of the capacitor. So luckily, we are now given a linear equation. It's not even quadratic. So equating its factor to 0 and simplifying, M1 will be equal to negative 1 over RC. That is after the transposition. So the complementary solution now, we'll go back here. We'll place the computed value of M. Should be Q1 e raised to minus 1 over RC times time or it will just be simply K1A raised to minus T over RC. This is now our complementary solution. Okay, let's try to bring out the particular solution. For the particular solution, this is the complicated part. As was discussed from the previous discussions, if the given right-hand side contains what we call this cosine function, for the particular solution, we will assume that there should be a cosine function, okay, cosine component and sine component. So I will place here I particular should be a constant A, cosine of omega t plus angle P, plus another constant B, sine of the quantity omega t plus angle P. Okay? We anticipate that there will be a cosine in sine function. So this is a cosine function, this is the sine function, but we do not know the value of A and B for the meantime. So let's proceed in the so-called computation of A and B. Taking the first derivative. A is constant times the cosine function, so it should be A. The derivative of cosine is negative sign, so this is now negative. Times the derivative of the angle, omega times 1, so this is actually the coefficient will now be A omega sine of omega t plus angle P, close quantity. For the second one, B is constant, this is a sine function, so it will be B times the derivative of sine, so it will now become cosine. But the derivative of the angle will be omega plus 0, or will just be simply omega. See, the coefficient on the second part will be B omega cosine of omega t plus angle P. Taking the value of IP and I prime P, we'll go back here. So I place it here, substituting. The value of the first derivative is this one. It is this. That's the first derivative. I'm following this. Plus 1 over RC times the value of the particular solution. The particular is A cosine, B cosine, but there is an RC over here. So I distributed 1 over RC immediately, so what comes out will be A over RC cosine of omega t plus angle P plus B over RC sine of omega t plus angle P equal to, the right hand side is actually omega E sub m over R cosine of omega t plus angle P. So this is actually the right hand side, the given right hand side. It's not given. What comes out after the manipulation? Okay. To solve for the value of A and B, this is now a part of algebra, since it's similar to the so-called solution of a partial fraction. So equating coefficient of like terms, there is a term that contains the value or the term sine of the quantity omega t plus angle P. So for all the terms that contains this one, we take the coefficients. For the first part, it should be negative AW. So this is negative AW. Second part, this is sine, this cosine, this cosine. Sine is this. So what will be next? The coefficient will be B over RC. This is B over RC. Right? For the right hand side, there is no sine function, so we will place that 0. And if we try to compute for A, A will be B all over the product of omega RC. We call this equation number 1. So we are now given equation number 1 involving A and B plus the constants omega, R, and C. Because for any given problem, these are given. Okay, let's proceed. Cosine of the quantity omega t plus angle P. Cosine of omega t is this one. The coefficient will be BW. So this is BW. Right? This is also cosine. The coefficient will be A over RC. So this is plus A over RC. Equal to, for the right hand side, we got the cosine term. The coefficient is the product of omega E sub m over R. So I will place the right hand side to be omega times E sub m over R. We call this equation number 2. To bring out the solution of this, it's a little bit long. Our bulletin board, our blackboard is not enough. So I just placed here solving equation number 1 and number 2 simultaneously. You could do your part, okay? If we try to compute for the value of A and B, A now will be omega C E sub m all over omega RC quantity square plus 1. And B will be omega C square times R E sub m all over omega RC square plus 1. These are the values of A and B. If we try to solve simultaneously equation number 1 and number 2, that is after the simplification. Oh, we lack space. I didn't show you anymore. And if we try to bring out the vector diagram of the impedance for an AC circuit, that contains a resistance and capacitance, this will be the vector diagram. This is the resistance, this is the capacitive reactance, and this is the impedance. X of C, this is X of C actually. X of C is actually 1 over 2 pi f C. Or this should be 1 over 2 pi f, 2 pi f C. 2 pi f is actually omega times C. So this side here is 1 over omega C. And using the Pythagoras principle, the square of the hypotenuse, which is the impedance square, should be equal to the resistance square plus the square of the side. I place it here, Z square equal to R square plus 1 over omega C quantity square. And if we try to simplify this one, omega CZ quantity square is actually omega RC quantity square. This is plus 1. We needed this relation in the simplification. Okay? Since we are now given the value of A and B, we will take the value of A and B, then we'll go back to the particular solution. So this is now A times cosine. This is now the value of B times sine. Okay? And if we try to simplify this one, I will not show you the complete thing. It's a long term. So this will be the continuation, that this will be E sub m over Z times open bracket 1 over omega ZZ cosine of omega t plus angle p plus the ratio R over Z sine of omega t plus angle p close bracket. And if we try to notice this one, the ratio of this side here over the Z is actually the sine of angle theta. So that's equivalent to sine of angle theta. And the ratio R over Z is adjacent over hypotenuse is actually cosine. So this value here, okay, is cosine of theta. Okay. So what will be next? It will be E sub m over Z. The expansion will now be sine of theta cosine of omega t plus angle p, cosine of theta sine of omega t plus angle p. And this is similar to the sine of the quantity A plus B. Okay? And if we try to expand this one, where A will be equal to omega t plus angle P, and B is equal to theta. Okay? So if we try to expand this one, substituting the value A and B to be omega t plus angle P plus theta, what comes out is actually this one. Okay? So meaning the expansion of this, if we try to compress it, it will be equivalent to the sine of the quantity omega t plus angle P plus theta. The first one is A, the sum of omega t plus P, and theta is actually B. Meaning if we try to expand this one, it is this. But if we try to compress it, it will now be equal to sine of the quantity omega t plus angle P plus theta. That's the particular solution. So this is now the importance of the so-called double angle sine function and trigonometry. I will check my camera. Okay, so there's a relevance of trigonometry over here. Without knowing that, we could not take the compressed value of this one. Because this expansion, if we try to compress it, it will be sine of the quantity omega t plus angle P plus theta. So the general solution now will be equal to, we are now given the particular solution, right? It's the particular solution. So the total general solution now will be the complementary plus the particular. So the complementary is Q1 A raised to minus T over RC plus the simplified particular solution. Okay? The simplified. Because this was expanded and we try to simplify it into the compressed one. It will be E sub m over Z times the sine of the quantity omega t plus angle p plus theta. So, okay, that's the general solution. So, we are not yet given the so-called particular solution. Let's try to compute for the value of K1. Okay, using the equation IR plus Q over C equal to E sub m sine of omega t plus angle P. That's what the original equation. Q over C is actually V sub C, the voltage across the capacitor. The voltage across the resistor is the product IR. The voltage across the capacitor is actually the charge over the capacitance. And this should be equal to E sub m sine of omega t plus angle P. At time t equal to 0, we assume that initial charge is equal to 0. Okay, so I sub 0 times R, I'm following this. Plus, if the charge is 0, 0 over C will be 0. And this should be equal to E sub m sine of angle P. No more omega, because we set the time t to be 0, so this will become 0. So this will now just be simply E sub m sine of angle P, right? And computing for the initial current at time t equal to 0, this should be equal to E sub m over R times sine of angle P. We needed this value to compute for the value of K1. So if we try to go back on the general solution, the initial current is actually E sub m over R sine of angle P as per computation. This should be equal to K1. When time t equals 0, this will become 0. A to the 0 will be equal to 1. So this is times 1. Plus E sub m over C sine of, at time t equal to 0, this will become 0, right? So what remains on the parenthesis is just simply angle P plus theta. So K1 now, K1 will be E sub m over R sine of angle P minus this value here. We transpose this on the left and we try to rearrange. This is minus. So the total particular solution now, we now know the value of K1. This is now the value of K1. Okay, we place it back it here, it is this, times E raised to minus T over RC, plus the second part, the particular which we computed already, that is E sub m over Z, sine of the quantity omega t plus angle P plus angle theta. So this is now the particular solution, that is current as a function of time. It's a little bit complicated. I think it is similar from the previous discussion, RL circuit. The only difference was this was minus and the transient part is a little bit different. But on the so-called particular solution, they were the same except that this was plus and from the previous discussion it is minus. Okay, that's it, guys. We are now given current as a function of time, considering a resistance and capacitance connected in series energized by an alternating current source. It's a little bit long. I is actually E sub m over R sine of angle P minus E sub m sine of the quantity angle P plus angle theta close bracket times E raised to minus T over RC plus the steady state part E sub m over Z sine of the quantity omega T plus angle P plus angle theta. This is the particular solution. Okay, for those who are taking advanced mathematics in connection with electrical transits, this is for you guys. Okay, if you want to subscribe to my channel, okay, please click subscribe. My channel is at youtube.com/@ProfDavidJ.Reyes. I got topics on differential calculus, integral calculus, differential equation in advanced math in lecture form. It's a long form video. This is the fourth subject matter. So if you want to subscribe to my channel, please click subscribe. And if you want to share to your friends, please click share. Good evening from Los Angeles.